Okay, hello everyone. Welcome to the International Methods Colloquium. I am Dr. Justin Essery, Assistant Professor of Political Science at Rice University. The International Methods Colloquium is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Rice University and the National Science Foundation. This week's speaker is Matt Lebo from Stony Brook University. Welcome, Matt. The talk is entitled An Effective Approach to Repeated Cross-Sectional Design. Matt's talk will last between 30 and 40 minutes, after which he will be available to take questions from the audience. You may call in to ask a question on the air at our toll-free call-in line, and I'm flashing that on the screen right now. 1-855-667-8287. That's 1-855-NO-STATS. You can also email questions to methods.colloquium@gmail.com. And if you are going to call in to ask a question, I recommend that you call in toward the end of the show once we ask for questions, because otherwise you'll just have to sit on the line for the whole time while we're waiting. But you can email me a question at any time. A copy of the slideshow that goes along with this presentation is available, and we're going to post that link in the little chat window that appears in your webinar, whatever it is, control panel. So you can scroll back and follow along with the older slides in the presentation if you want to. You can see that just posted right there. Without further ado, Matt, welcome to the International Methods Colloquium.
Okay, thanks a lot, Justin. So, so the paper is available on my website. It's this came out in the AJPS this issue. It was in my mailbox yesterday. So this is good timing. The R package that goes along with it is written by Patrick Kraft, Chris Weber, and that is available as well on my website. And Patrick's here, and he'll talk about it just for a few minutes at the end of the talk. Let me start. Okay, so I wanted to talk about panels, pseudo-panels, and repeated cross-sectional designs. What are the differences between those? So we know that panels have the same observations at multiple points in time. Pseudo-panels do not have identical sets of cases at every point in time, though things can be repeated, such as looking at a congressional data set where some people appear in multiple Congresses and some people appear in only one Congress. But over the course of congressional history, of course, we have people leaving and people coming and going. An unbalanced, so that's one definition then of an unbalanced panel with some observations appearing more than once. A repeated cross-sectional design will not have any observation appearing more than one time. How prevalent are repeated cross-sectional data sets? They are very prevalent. Okay, so the cumulative NES file, for example, the National Annenberg Election Study, the General Social Survey. We could go to the ICPSR archives and pull out monthly surveys going back to the 70s of CBS New York Times polls. If you have if Gallup wants to cooperate, they could give you over 1,000 of their individual level surveys. There's world value surveys, the Michigan Survey of Consumers. All of these things over and over again are repeated cross-sectional surveys. So we looked at APSRs and HAPSs from 2010 to 13, and we found 42 articles that have some type of repeated cross-sectional structure. And of course, the ones that I just named are the public opinion examples. And in the paper, we have examples that aren't public opinion examples. There are lots of other examples of things that are many cases nested in time where the time structure matters. So votes within over the course of congressional history that are nested within different Congresses, and the point in time in which those votes occur makes a difference in how we should estimate the model. So a true panel has the same person or country or state appearing in multiple years. So Y11 there is the same in year 1, year 2, year 3, and so on. A repeated cross-sectional design has individuals nested in time, so Y11 is not the same person as Y12. The first person that's called it by Gallup this month is not the same person that they called last month or next month. So we have multiple strategies that we could use with a repeated cross-sectional design. So let's suppose we have individuals that separate set of individuals at T1, T2, T3. One solution is to just go aggregate. to use the daily means for the time series. Here the mean of the first period, the second period, the third period, and do a time series analysis that is simply t units long. So traditional long t time series, we would use the mean of y, model it using the mean of x. It allows us to study political dynamics. There are lots of advantages to this. It overcomes partisan bias at the individual level. So Kramer talks about that. It allows time series methods like co-integration, time-varying parameters, and of course many key pieces of political research, including major studies of public opinion, are time series analysis studying public opinion over time. So studies that begin with repeated cross-sectional time series and then create time series from them, McHugh, Erickson, and Stimson use Gallup polls, Box, Steffens-Meyer, Buffett, and Lynn's gender gap paper, uses CBS New York Times polls, Clark, Stewart, Alton, Elliott use the Michigan Survey of Consumers, Johnson, Hagen, lots and lots and lots of examples. Time series analysis in public opinion almost always starts with repeated cross-sectional data. Another option is to just naively pool all the observations together and use the individual level data, pool it all together as though they were all taken together at the same time. All the surveys were taken together at the same time, and there are lots of examples of people doing that. So this gives us the ability to look at cross-sectional hypotheses, but not to look at dynamics. All right, so now, what are the problems with repeated cross-sectional data? Really, most of what I'll talk about today, especially the method, applies outside of repeated cross-sectional designs. It applies to panel data as well, but for the most part, we're more concerned, at least for now, with repeated cross-sectional papers and data sets because the range of solutions is so limited there. Okay, so in a true panel, we have autocorrelation going in two directions. First, within a specific time point, we have correlation going on because these things are taken at the same time. So solutions like fixed effects or panel-corrected standard errors try to account for the fact that the errors that occur within a specific time point have more to do with each other. We also have correlations due to specifically to individual I. Okay, so this individual remains the same individual over time, and the errors for that individual may be specific. And we have solutions like lag-dependent variables and differencing. So we could look at, in a panel, how this individual one is different this time than last time. We could difference or have a lag-dependent variable or something like that. So again, autocorrelation going on in two directions. What changes with repeated cross-sectional papers is the range of solutions. Okay? We cannot use a lag-dependent variable because y for individual y in this month's data set, t-1 doesn't appear in the data set. We can't difference the dependent variable or independent variables for the same reason. And even if we could do these two things, then the methods might be insufficient to account for the between-wave memory. Panel-corrected standard errors are premised on a true panel. They don't solve the bias if it exists. Fixed effects don't solve autocorrelation in either direction. So, does the problem of autocorrelation go away because these observations occur only once? And the answer is no. So let me try to explain why that's the case. In a repeated cross-sectional design, we still have autocorrelation going on because of observations that are nested within the same survey. Okay? So these things that are specific to time point t still cause autocorrelation. But is the error from one survey still correlated too much with the error from the following survey, even when they're not the same individuals? And the answer is absolutely, they're still correlated with each other. So if I try to rephrase that, do we expect correlations? I'm sorry, there's an awful lot of text here. I'm not going to read it all to you, but you can come back to it. Do we expect correlations between y, the mean of y at time t and at time t plus 1? And of course, we do expect there to be a correlation there. And there are many, many papers in the time series literature that look at autocorrelation going on in aggregate studies of RCS papers. So if they're correlated, then the errors at time t are more correlated with the errors at time t plus 1 than they are correlated with the errors at time t plus 2. Okay? So since observations in each time point are dispersed around a mean that's correlated with the mean at the next time point, then we have autocorrelation that at the individual level carries on from one time point to the next. So there's a little bit of the math there to explain that. Okay, so the correlations are still persisting even, right? So the people in this month's survey, still the errors are more correlated with people from last month's survey than they are with people from 2 surveys ago. So how do we deal with these 2 types of autocorrelation? The available methods don't provide a solution since we can't difference or use lag-dependent variables, panel-corrected standard errors, fixed effects, random effects. Special effects cannot get rid of the autocorrelation. All right. Then an older question is, how do we choose a level of analysis when we've got repeated cross-sectional data? Should we be looking at the individual level data and looking at important cross-sectional effects, or should we be looking at the aggregate level and time-varying effects or hypotheses that vary over time? Do we cut out a wealth of information that's going on at the individual level and study aggregate time series? So there are people who defend that and there are reasons to prefer time series. McHugh and Erickson, Stimson and Kramer talk about, if there's endogeneity that goes on, how people view the economy is dependent upon their own partisan viewpoints. And if we go up to the aggregate level, then all of those individual level biases should cancel each other out. That's what Kramer talks about. Or do we ignore all of these dynamics, throw everybody together, use cross-sectional techniques and maybe some set of fixed effects to try to account for that? So our method is premised on let's do both. Let's look at the aggregate level, let's look at the individual level, and let's make sure that we're accounting for the autocorrelation problems so that the inferences that we get at the aggregate level especially are protected from problems due to autocorrelation. Okay, so to do this, we use an autoregressive fractionally integrated moving average multi-level model. So the ARFEMA methods are familiar to time series people, perhaps. They're a generalization of ARIMA methods, multi-level models most people will be familiar with. We marry these 2 things together. We're not the first ones to use a multi-level model for time series data, but we think that we're solving autocorrelation problems at level 2 much better. So we can think about level 1 units, people, votes in Congress, Supreme Court cases nested within years, as situated within level 2 structures, days, months, years, etc. So there's a couple citations of people who've used MLMs with pooled cross-sectional time series, but they're not dealing with autocorrelation, or they attempt to fix it with a lag-dependent variable. We cannot fix ours with a lag-dependent variable since we don't have it at the individual level with repeated cross-sectional data. So the multi-level model relies on the assumption that errors are spatially and temporally independent, and so we have to deal with autocorrelation before we estimate the MLM. All right, so again, our solution works for pooled cross-sectional time series, but it's especially useful for repeated cross-sectional data sets because it has less competition. It has less competition there than it does in the PCSTS toolkit. All right, so we look at individual observations. They're embedded within multiple sequential time points. We want to retrieve estimates at the individual level and at the aggregate level. We want to allow some variables that vary only within cross-sections and some that vary between cross-sections. So for example, our multi-level model can have at level 2 something like the unemployment rate, right? Something that doesn't vary across individuals, but it happens only at level 2. And we want to use the best available techniques in time series analysis to make sure that we've properly dealt with autocorrelation at level 2. So our technique we call double filtering to clean up the 2 types of autocorrelation that are going to be particular to RCS data. All right, so let's go through some of the math of double filtering. It begins with level 2. Okay, the ARFEMA part comes before the MLM part. So the ARFEMA equation here, y is some aggregate level time series, or y bar is the mean of some variable that varies across individuals and across time. So the Arfima equation for a long T-series has autoregressive parameters P, it has Q moving average parameters, and it has D is the fractional integration parameter, which tells us how many times Y needs to be differenced in order to make it stationary. And that 0 makes it an ARMA model, 1 makes it an ARIMA model, somewhere between some non-integer value makes it a fractionally integrated model or an Arfima model. So we can estimate the correct values of P, D, and Q to create white noise residuals. So this is, estimating P, D, and Q and choosing a model is a tricky prospect. We're doing that in R. Depending upon what parameters you ask, I'm getting off into many other papers here. Depending on what parameters you ask to get estimated, you can get different answers. If a model is truly fractionally integrated, but you want to see if you can capture that just with P and Q parameters, then usually the statistical package will oblige you. The R package that we've got, we're estimating D usually in a 0D0 model. We can look for extra parameters if we like. We use that model. We estimate what D is. We use that to filter it. We get white noise residuals. I said quite a bit of this in the last slide. So where D equals 1, the model simplifies to just a difference model. Where D equals 0, the model simplifies to a stationary ARMA process. Okay? So more cross-sections make it easier for us to get an estimate of D. In the paper, we talk about having a minimum of 50 cross-sections to use the Arfima framework. If you get below 50, then we could look simply for an ARMA model or an ARIMA model, which are approximations. With some different estimates of D, you can estimate D with T smaller than 50, but 50's in our R package, that's about a recommended floor for the number of cross-sections. But still, when you get down, again, when you get down to perhaps into the 20s for the cumulative NES file, then an ARMA version or an ARIMA version of what we're talking about makes sense. So with the first filter, we make a noise model for level 2. All right, so here we create Y bar star, which is the residuals from Y bar T regressed on its noise model. So this is a series that's stationary in the long run, free from autocorrelation due to short-run autoregressive and moving average processes. Then we do this separately for X and Z. Okay, so we refer to X's or independent variables that vary across individuals and across time. And Z we think of as variables like the unemployment rate that are only existing at level 2, don't vary across individuals. So we take each one of the series in our model, we figure out its own D parameter, and we filter it so that we get Y bar star, X bar star, and Z star. So this is now level 2 data that is cleansed of autocorrelation. And if you were only going to do time series, this is what you want to be doing. But the second filter, if you want to use individual level data as well, we look at the deviations from daily aggregates noise model. Not deviations from the mean, but deviations from the noise model. So if there's autocorrelation at level 2, then centering around those daily means would not solve the autocorrelation at level 1. All right, so at the bottom there it says center YIT around Y bar star T. Okay, so using just daily level data, such as Y bar T or Y bar T minus 1, may not be enough to properly control for autocorrelation. So we have to do this individual level second filter around those daily means. So we create lowercase y star star as the deviation from the aggregate noise model. All right, and at the bottom there it says this creates individual level observations that vary both within and between days, but through double filtering are cleansed of autocorrelation and safe to be included in a multi-level regression. So now we can estimate the multi-level model. We've properly transformed all of our data. We can look at the level 2 equation as y bar star predicted by x's again. The means the filtered means of x's that vary across individuals and those that vary only across time. And the level 1 equation gives us the within variation. Or we can estimate these two things together and get aggregate effects with beta 2 and individual level effects with beta 1. So points of flexibility here. Depending upon the length of t, again, we can use ARMA, ARIMA, or ARFEMA models. If the model, proper models are just 0, 0, 0, 0, then the model reduces to mean centering. And potentially we can include time-varying coefficients. All right, so we use the individual level data to tell us about how, over time, a coefficient is evolving, and we do that while safely accounting for autocorrelation. So that's the delta parameter there. It's applicable to PC STS as well, as I've said a couple times. All right, so let's look at some Monte Carlo analyses to see whether or not we're making type 1 errors. We know the added value of estimating these two things together, but have we solved the two directions of autocorrelation? We expect greater time dependence in level 2, and that the greater the level of time dependence in level 2, the more bias that we'll have in our coefficients. All right, so let's look at the Monte Carlo setup. We generate level 2 time series with different levels of memory serial correlation. We aggregate values. These aggregate values give us the mean for distribution from which we draw individual level data, and we do this for the x's and y's. We also generate data with no serial correlation to serve as a baseline for comparison. So we test a number of different approaches: naive pooling, lag-dependent variables with OLS, OLS with ARFEMA, MLMs with the day-level lags, and MLMs with our double filtering method, ARFEMA MLM. I should skip along a little bit and show you, as everybody's seen before, that the Monte Carlo simulations generally work the way that the author wants them to work. And they do here. Okay, so our MLM approach solves quite a bit of our problems, and let's skip to where the graphs are already. No. Simulation results, we measure it in a couple ways. We look at the RMSE and we look at the optimism index. You can come back to those. Okay, so here's essentially what we're looking for. The OLS ARFEMA is okay, but doesn't solve all of our problems. Really, it is OLS ARFEMA. I don't have the MLM ARFEMA here, but in the paper, figure 2, I think, shows you that these problems of bias are solved with the ARFEMA MLM. Okay, so we have also, here's the optimism index for 6 different approaches, and as D gets longer, as our memory gets longer, as autocorrelation gets longer, then OLS becomes much more problematic. These numbers, if there's no bias, then the numbers should be right around 100. OLS with a lag-dependent variable is terrible from the start. ARFEMA OLS is not particularly good, but all of our problems are solved really in that last column. Our optimism index never gets different from 100 essentially. Okay, so here as we get into longer and longer memory, this would be a unit root process here. Here these are longer levels of fractional integration. Then we've got enormous problems and lots of type 1 errors unless we switch to an ARFEMA MLM framework. This would be true if we were doing strictly time series or if we were doing something like a multi-level model or anything without properly counting of level 2 autocorrelation. So here's 3 examples of repeated cross-sectional data sets in action. So Hopkins 2012, Whose Economy? Perceptions of National Economic Performance During Unequal Growth. So Hopkins has lots of data and wants to use all of it. There's 215,000 respondents that are nested in 388 months of data from the Michigan Survey of Consumers. And Hopkins wants to use it all, and that's great. So in the aggregate, though, these series have been shown to have long memory. And when you aggregate up the Survey of Consumers, various studies have shown that there's high levels of fractional integration. So that was shown in Bach, Steffensmeyer, and Tomlinson had the 2000 article. It's been found in several places. The key hypothesis, though, is not at the individual level, it's at the aggregate level. Americans at all income levels weigh income growth at the low end in their responses. So it's a level 2 conclusion, but there's problems going on at level 2 that this long memory should worry us with. We should worry about. So the key effect, though, that we see, we can't retrieve it once we control for that autocorrelation. So this is just the t-value on that key hypothesis test. So if we use just the MLM with a lagged dependent variable, then we get inflation in the t-statistic, whether it's for rich, middle income, or poor, and that t-statistic is quite high. Hopkins' version of, he does use a multi-level model, but without the level 2 fix, and that leans towards type 1 errors as well. When we account for level 2, when we do our double filtering method, then we can't retrieve that effect. The t-statistic isn't statistically significant. Okay, so as you would see in a study that is strictly aggregate time series, if you're not taking account of autocorrelation, then you're more likely to reject the null hypothesis. And that's true once you switch, of course, to using the individual level data that's nested in time, and you have many multiple time points. A second example, Lebo, McGlynn, and Koger. So that paper, Strategic Party Government, is a study of, the original study is time series, right? So we took 210 years of data on congressional roll call votes and aggregated them and looked at the interaction between Republican Party voting and Democratic Party voting as a whole. But really, there's 29,734 separate roll calls that were nested in those years. And there's some things going on at the individual level that we might be interested in. So again, in that original paper, the finding was that those two series are fractionally integrated, and something has to be done to account for that at level 2. In this example, in this paper, we tried time-varying hypotheses as well to see, we have this wealth of data going on at the individual level, and we should be able to look at how coefficients vary over time. So what we find, though, is that in our polarized, that the time-varying hypotheses, show changes in time over how strong the two parties are interacting with each other. In the polarized era now, there's very little variation in unity across votes. So there's not much within Congress variation or interaction. So what we get from our FEMA MLM model of this is we see that within-year effects are really strong, that the minority party has a strong effect on how the majority party is voting together, right? So this coefficient tells us when the minority party votes more unified, the majority party counters that. And we see at the aggregate level, so this is really what the Lebo, McGlynn, and Koger paper has, is this part where minority party and majority party are in this long-term interactive relationship with error correction going on over the 210-year, here we updated the data, 217-year period. So we have two things going on, the individual level and the aggregate level. And then we can also estimate the time-varying effect. So this solid line tells us what the effect is just using the time series data, right? So if we were only to use a time series model, we would think that the effect is constant over time. The effect is about here. By using the roll call level data and time-varying, our time-varying estimator, then we're able to see how that's changed over time. And you can see that, the effect of the minority party on the majority party is no longer as strong as it used to be. That really in this era, because partisan politics is so strong, we're way below the general tendency. People are voting strongly with their party regardless of what the other party is doing. And so really the important effects are still are across time and not so much within Congresses. Our third example looks at the Annenberg data, which is just of course, a repeated cross-sectional study, or in this case, it's a rolling cross-sectional study because we do not use the terms rolling cross-sectional and repeated cross-sectional interchangeably. The Annenberg study is rolling in the sense that they decide before these studies who they're going to contact, and then they roll out the surveys over time with specific dates. So here we model campaign effects of evaluations on Obama minus evaluations of McCain. Our multi-level model has within and between effects. And the economic effects are really complicated. I'm not going to explain them all. They're very complicated, and we can see a lot of nuance when we look at the individual level data versus the aggregate level data, and we can also see we estimate some time varying effects. So this is a big table, and we see some of the effects going on across days and some going on between days, and I'll just show you the last. This is the nice time varying effect that we can see over time. So the effect of economic evaluations are diminishing over the course of a campaign, or more interesting maybe is the graph on the right, which just shows party identification being activated over the course of the campaign. How important is party ID in predicting evaluations of the candidates? You know, that's steadily increasing over the course from June to Election Day. And this solid line here is what we would see if we just estimated this as a static regression. Right? We wouldn't see this interesting variation over time. All right, so the limitations of this method. For now, if you'll notice, the examples that I used have continuous dependent variables. We're working on a model for dichotomous variables at the individual level, but the math is not going to be exactly the same here. So all of these are with continuous dependent variables. The length of t should be at least 50 with the estimators we're talking about, but 40 potentially with other estimators that we're looking into. And if you move away from, get below 40, then we can talk about ARMA or ARIMA. So the cumulative NES is too short, but you should still be keeping these things in mind. If you're doing something, you should be worrying still about what's going on at level 2, even with data as short as the number of waves in the cumulative NES. All right, so I want to have Patrick Kraft, who's here, talk a little bit about implementing this with our package. And to do that, I'm going to unplug my earphones, and maybe that means there'll be a little bit of feedback. Okay, go ahead.
All right, should I just stay here?
Scooch over a little bit.
All right. Yes, so we wrote a small R package called our MLM to basically facilitate the implementation of the method that Matt just described. And it basically performs all the procedures that we talked about so far, and the analysis, the subsequent analysis, based on a single function call, just to basically as a convenience function to make it easier to use this method. In order to do that, it uses several other packages that are available in R and on CRAN. Fractal and FracDiff are two packages that are used for time series analysis, and that we use in order to do the fractional differencing. And MLE4 is a function in order to estimate the multi-level model. So in the package that we wrote, we have currently three major functions. One is our MLM, which is the main method, basically, which implements the double filtering first and then estimates a multi-level model. Then we have our OLS, which does, again, the double filtering, but estimates an OLS model instead of the multi-level model. And then our prep, which is essentially a function that implements all the data preparation, the double filtering and everything, but doesn't estimate the model itself right away. So that can be used in order to do just the data preparation and then do the model estimation separately. So we can go to the next slide. So this is just a basic example of how the command looks like in the end. I don't want to go into too much detail about the command structure. Whoever is knows multi-level modeling in R might be familiar with the might be familiar with this formula specification where you can specify the multi-level structure when calling, for example, LMER. So our MLM uses the same formula structure, but what is different to a regular multi-level model is that we have additional suffixes that we can add to the variable names in order to call specific functions. Okay, So for example, what we have here is .ydiff. This is not part of the original variable name, but it's basically a call that tells our FEMA MLM, the function, to implement the double filtering as specified previously. xdiff, added to an original variable name, calls for just mean centering for each time point in the data set. And then we have fd, .fd, which implements fractional differencing for level variables in the data set. Okay, so this is the basic structure of the command. I don't want to go too much into detail. There is also a documentation online that describes further options that can be specified. Okay, so this is just a very quick example of the output, how it will look like in R after we estimated the model, and basically called the summary. And it basically consists of two or more parts. The first part here is the fractional differencing parameter, so it summarizes the fractional differencing parameter that we estimated in order to implement the double filtering. And then summarizes, in this case, it was our FEMA OLS. This would be a multi-level model if we call it our FEMA MLM, and then just estimates the parameters, not with the original variables, but with the variables where we implemented the method, meaning the double filtering or fractional differencing for level variables, and so on. So our FEMA MLM is available on CRAN, so it can be just installed just like any other package. And the development version is also available on our GitHub, and you will also find further documentation there.
Okay.
All right.
Okay, now we find out if anybody was actually listening, or if I made some tragic mistake along the way. Okay, Justin, are you there somewhere?
Yep, I'm here. I assume that means the talk is over?
Yep.
Okay, well, thanks very much, Matt, for that talk. And at this point, we've got about 20 minutes for Matt to take questions from the audience. Let me flash the information up here. You can call toll-free at 855-667-8287. That's 1-855-NO-STATS. It's toll-free in the United States only, I should say. I have no idea how 800 numbers work outside the U.S. And you can also email questions to methods.colloquium@gmail.com. And it turns out we already have a question from Foya Apedin von Hau. Foya says, thank you so much for this presentation. I'm curious to hear whether this model addresses problems if the data is strongly unbalanced.
If it's strongly unbalanced, meaning that the size of the waves is quite different? Is
that's one possibility. The other possibility is some sort of missing data problem. I mean, when I think about unbalanced panel data, usually what I'm thinking about is there being a lot of missing data at various points.
Well, yeah, I think of unbalance as meaning that different observations may be appearing different number of times, and that the size, of course, can be different, and that's okay. I mean, it depends what kind of data set we're talking about. If we're talking about number of roll calls situated within Congress, then of course Congress has a different number of roll calls each year. There's different number of Supreme Court cases each year. They do not have to be the same size at all. It would be there will be some trouble if, say, there are some time periods with no observations, because that will affect really our estimates of what's going on at level 2. So if we had something that was going on, that there was nothing going on at level, there were no observations for some of those time points, then our time series at level 2 will be our estimates of the autocorrelation there will be strange, and I can't think of an example of what might do that. But I would say as long as we have at least one observation for each time period, then then we should still be able to do estimates at level 2. We should still be able to do the second filter at level 1. If we really were missing observations for an entire time point, then I suppose we could you could interpolate level 2 values for that one time period and not have individual observations.
I'm thinking about, so in a normal panel, when you've got multiple units and multiple times, some panel time periods being missing can be a big deal. But in your case, you kind of, in some ways, are getting rid of that problem, because if a few individuals have partially missing answers or something in a survey, well, I guess I should ask, is the fact that you're in some sense averaging these at level 2 gonna deal with that in a way that's more effective than if you just had
maybe it's okay, so that's a better example. So if it's a panel, and so some countries don't report something in some year, so maybe this is better, because if our solution for panels is to difference, and if you haven't got last year, then you can't get the difference for this year. With this method, when you're filtering the level 1 data, then you just that drops out as missing for the specific year. But it shouldn't prevent estimates for the data that you do have.
Well, thank you for that question. We have another question from Jeff Harden. Jeff says, "Hi Matt, thank you for the interesting presentation. Usually two-stage estimators require some adjustment to the standard errors to account for additional variance. Does that apply here?"
Hi, Jeff. No. So the estimates of the standard errors are just, they're fine, and they're appropriately sized, and we check that with the RMSE and the level of type 1 errors and so on.
Well, thanks for that question, Jeff. I have a few questions I wanted to ask. Okay. So one of the things I was thinking about is, if you've got repeated panels, you can think of there being different, I'm sorry, I shouldn't say repeated panels, but rather you've got observations of a population over time, but there are different people sampled in each time, which is your key problem. You can think of there being possible subpopulations inside of that population. So just a trivial example, Democrats and Republicans in a political survey. Or if you're doing cross-national surveys, there are different not only different countries that are sort of subpopulations, but there may be subpopulations inside of those countries. And I'm wondering if it's plausible that the degree of autocorrelation or integration inside of those subpopulations is different. And if that's true, what consequences is it going to have for your estimator, which I guess would try to average over the two subpopulations?
Sure. I mean, it's quite possible. The measure of anything that you're aggregating up. So the Michigan consumers data, we might have different levels of fractional integration for economic prospections for Democrats or Republicans, or for men versus women. And when we are putting everybody together at the same time, then we get just a single estimate.
So does it matter? Like, do we have to worry about that?
Well, now I do.
You're welcome.
I don't think so. I mean, it might be something that's a good question.
I mean, one way I could think of, so I'm going to try to solve my own problem now. One way you could think of dealing with it is, well, if you've really got two subpopulations, you should create two second-level averages, right? So you're basically building in some sort of you're kind of restoring a quasi-panel structure. So I don't see the same guy every year in my survey, but I do see some Democrats every year in my survey. And you can create a sort of a pseudo-panel of Democrats and then calculate how they are integrated, how they're autocorrelated, whatever it is you're interested in at that level. That's
Well,
you'd have to have a big enough sample, but
right. So, and the problem is, as samples get smaller in repeated cross sections, then your estimates at level 2 get more difficult. So that's a problem with the Annenberg study, for example. So when the daily samples are only 70 people or 100 people at the most, then a great deal of the day-to-day variation is just survey error, and that drives down our estimate of memory quite a bit. So if you might want to think, how does party identification vary from day to day over the course of a campaign? It looks like it varies quite a bit more than you would think, or that there's shorter memory with partisanship, because there's so much survey error and it just bounces around a lot more than we would hope. So if our samples were big enough, if the waves were big enough, then yeah, you could break it out and look at differences in the estimates. And of course that's something that people do with time series data. We look at the difference in memory between Democrats and Republicans, or between men and women, and so on. What are the consequences of aggregating them together with the individual levels? So our filtering is based around the grand filtered value rather than this group-specific filtered value. With most things with fractional integration techniques, you're fixing a great deal of the problem by filtering it to begin with. So if you filter it by 0.8, that's a huge improvement, even if you should really be only filtering it by 0.75 or 0.85. So there are, you want to get it exactly right, but you're already making a huge improvement, just even if it's a little different because of a specific group.
And this actually leads to another question I had, which is, so you're very careful to note that you're very careful to note.
Brother shopping. Yeah.
Yeah, I see that. You're careful to note that you need a sample of sufficient length in order to extract, for example, a fractional integration parameter, and it's good. What I'm wondering is, okay, so what if you try this and your model is, so the Monte Carlos are very good at saying, if you use this model on a correctly specified DGP, it works. If you use a simpler model on my DGP, it doesn't work, right? That's the classic Monte Carlo demonstration. What happens if you use your model incorrectly? In other words, if it ends up being incorrectly specified, are there any kinds of how severe are the consequences, for example, of trying this on a data set that's too small or too short for it to work, or alternatively trying it on a data set that really doesn't have this kind of dynamic structure and you're trying to force it to have the dynamic structure?
I think you would have to make a major mistake somewhere along the way. So if there's very little memory from one wave to the next, then somewhere you should notice that. You would get a very small estimate of D. It would be close to 0, and so long as that our estimate of D is 0, then really the level 2 filtering is nothing. If it's really 0, then you're not filtering at all. Then it's just mean centering, which is fine. So you would have to make a mistake somewhere along the way that you are filtering it by an inappropriate amount. You'd have to have a bad estimate of D. So potentially, mistakes that you might make is it's an autoregressive series, and it's strictly an autoregressive series, but you estimate it to see if it's fractionally integrated. So you wind up estimating a 0D0 when really it's a P00. The differences in filtering, there's some differences there, but they're not huge. And even if you get that, if you're estimating P instead of D or D instead of P, you're still making a big improvement on compared to leaving it alone. But estimating something at the aggregate level is something obviously people are still debating about what's the best way to do that. And the more time you spend trying to figure out what's the real level 2 process going on, the more informed you'll be in making that modeling choice. So do lots of, if your series are long enough, you can do all the things that you should be doing with time series data, looking at autocorrelation functions and partial autocorrelations functions, and looking at other literature and trying to see whether is this really fractionally integrated or might it be something simpler. If you have enough data, enough waves, you can do that. And then that would help inform you about what you should be, how that first filter works, and then the second filter around that.
Mm-hmm. Okay. Looks like we don't have any more questions right now, and so we're almost at the end of our time anyway. So I want to thank Matt for his presentation this week. Thanks to Matt Lebo of Stony Brook University for a very interesting presentation. Next week, tune in at noon Eastern, 11 Central, for a presentation by Susie Lin of Penn State University entitled "Treating Time with All Due Seriousness." And if you're interested in taking a look at that, I should be able to flash up a thing. Maybe I can't flash up a thing. Here we go. You can check out our website, www.methods-colloquium.com. You can sign up to participate in next week's IMC and get notifications about future presentations. We have a whole slate of presentations this year running out to April. You can even sign up to participate this year or in the next academic year if you want to give your own talk. Matt, thank you very much for presenting. And Grant, is that you in the background there?
No, that's Patrick.
Patrick, I'm sorry. Patrick, thanks very much for your presentation. And see you next week.
Thanks, Justin.
Thanks.
See you, Matt.